everyone, in this video I'm going to discuss regression trees in which the target variable is numerical. In the previous videos I presented classification trees where the target variable assumed a categorical variable. Like classification trees, regression trees can be constructed using the CART algorithm. The CART algorithm operates similarly for classification and regression trees except the following three differences. First, the target variable is numerical in regression trees, whereas it is categorical in classification trees. And the predicted value is the average value of the cases that belong to the same leaf node in regression trees. Second, we use mean square error rather than the Gini index to measure impurity. The higher the mean square error, the higher the impurity in regression trees. Third, the three performance measures are root mean square error, mean absolute deviation, mean absolute error, mean percentage error, and mean absolute percentage error in regression trees. Here on the screen, you see the balanced dataset. This dataset is composed by Hayden. If you remember, Hayden and his team built a dataset for predicting new customers which are likely to respond to Hello offers from Sunnyvale Bank. And now next they are interested in another predictive model that can help his team to identify and focus on high-value customers. And high-value customers are defined as those who routinely maintain high balances in their accounts with Sunnyvale Bank. In this dataset that he compiled, we have the worksheet balance data and balance score. Balance data worksheet contains the information from 500 current customers, including the customer's age, in years, sex, annual income, and the average monthly account balance. Balance score, on the other hand, includes the information of 20 potential customers, and this dataset includes the customer's age, sex, and income. Ultimately, Hayden wants to build a predictive model using the data of current customers to predict the average account balance for the 20 potential customers. Before building a prediction tree, we first learn how to identify possible split points using a smaller dataset. Therefore, here on the screen, you see a small dataset of 20 randomly selected bank customers from the balance data worksheet. And now we will select the optimal split for the age variable based on mean square error impurity measure. Here I sorted the age variable in ascending order, and also I copy paste this age column here in column O. And in this column, I deleted multiple occurrences of the same observation. And we are going to use midpoints between the consecutive values of age to determine possible split points. Here, the first split point is calculated as 18 plus 20 divided by 2, which is equal to 19. And the second one, 20 plus 24 divided by 2. And the remaining possible split points are found in a like manner. Now, let's consider the two possible splits when age is 30 and when age is 32. We will compute and compare the mean square error for the two split values to find the preferred split. Remember that mean square error is the average sum of the square differences between the actual account balance and the predicted account balance in each partition. A split at age 30 creates two partitions. Customers whose ages are less than 30, in that case we have 8 observations, and customers whose ages are equal to or greater than 30, in that partition we have 12 observations. The average bank account balances of the first partition is equal to $7,811.25, and the average bank account balance of the second partition is equal to $4,445. This suggests that if we create a regression tree with one decision node that splits age at the value of 30, all potential customers younger than 30 years will have a predicted balance of $7,811.25, whereas all customers 30 years or older will have a predicted balance of $4,445. And next we are going to calculate mean square error for the first split point when age is equal to 30. So here on the screen we have two partitions. We first calculate the squared differences. So here, as you see, we take the difference between the actual balance minus the predicted balance, and then this difference is squared. And we repeat this calculation for the 8 observations we have in the first partition. The mean square error is calculated as the average of all these squared differences. And we repeat the same steps for the second partition. We first take the differences and square. And finally, to find the average, we use the average function in Excel. Here, as you see on the screen, mean square error for the age less than 30 years old is 49,087,572.2, and mean square error for age greater than or equal to 30 is 14,209,843. Now we are going to repeat the same steps for the second split point when the age is less than 32. In the first partition, this time we have 9 cases. And the mean squared error, you take the average of all these squared differences. For partition 2, and here we calculate the mean square error as the average of squared differences. To compute the overall mean square error for the split, we calculate the weighted combination of the mean square errors using the percentage of cases in each portion as the weight. So for the first partition, we have 8 divided by 20 times the mean square error for the first partition plus, and here we have 12 over 20 because we have 12 observations in the second partition times the mean square error of the second partition. Similarly, a split at age is equal to 32 creates 2 partitions as well. Customers whose age is less than 32 and customers whose ages are equal or greater than 32. The overall MSE for the split is calculated as weighted combination of the mean square errors using the percentage of cases in each partition as the weight. The MSE value of the age is equal to 30 split is slightly smaller than that of age is equal to 32 split, suggesting that the age is equal to 30 split generates a lower level of impurity. Therefore, age is equal to 30 is a better split for constructing the regression tree. In fact, if we compute the MSE values for all the possible splits for age in our example, we would find that the split at age is equal to 30 produces the smallest MSE. Therefore, the age is equal to 30 split is chosen as the best split for age. So here on the figure you can see the regression tree when the age is the only predictor variable used in our analysis. As I mentioned earlier, the recursive partitioning process used for classification trees also applies to regression trees. In the following video, we will now develop a prediction tree with analytic solver.